In statistics, originally in geostatistics, Kriging or Gaussian process regression is a method of interpolation for which the interpolated values are modeled by a Gaussian process governed by prior covariances, as opposed to a piecewise polynomial spline chosen to optimize smoothness of the fitted values. Under suitable assumptions on the priors, Kriging gives the best linear unbiased prediction of the intermediate values. Interpolating methods based on other criteria such as smoothness need not yield the most likely intermediate values. The method is widely used in the domain of spatial analysis and computer experiments. The technique is also known as Kolmogorov Wiener prediction. The theoretical basis for the method was developed by the French mathematician Georges Matheron based on the master's thesis of Danie G. Krige, the pioneering plotter of distance-weighted average gold grades at the Witwatersrand reef complex in South Africa. Krige sought to estimate the most likely distribution of gold based on samples from a few boreholes. The English verb is to krige and the most common noun is kriging. Both are often pronounced with a hard G, following the pronunciation of the name Krige. Main principles, related terms and techniques. The basic idea of Kriging is to predict the value of a function at a given point by computing a weighted average of the known values of the function in the neighborhood of the point. The method is mathematically closely related to regression analyses. Both theories derive a best linear unbiased estimator, based on assumptions on covariances, make use of Gauss-Markov theorem to prove independence of the estimate and error, and make use of very similar formulae. Even so, they are useful in different frameworks. Kriging is made for estimation of a single realization of a random field, while regression models are based on multiple observations of a multivariate data set. The Kriging estimation may also be seen as a spline in a reproducing kernel Hilbert space, with the reproducing kernel given by the covariance function. The difference with the classical Kriging approach is provided by the interpretation. While the spline is motivated by a minimum norm interpolation based on a Hilbert space structure, Kriging is motivated by an expected squared prediction error based on a stochastic model. Kriging with polynomial trend surfaces is mathematically identical to generalized least squares polynomial curve fitting. Kriging can also be understood as a form of Bayesian inference. Kriging starts with a prior distribution over functions. This prior takes the form of a Gaussian process. Samples from a function will be normally distributed, where the covariance between any two samples is the covariance function of the Gaussian process evaluated at the spatial location of 2 points. A set of values is then observed, each value associated with a spatial location. Now, a new value can be predicted at any new spatial location, by combining the Gaussian prior with a Gaussian likelihood function for each of the observed values. The resulting posterior distribution is also Gaussian, with a mean and covariance that can be simply computed from the observed values, their variance, and the kernel matrix derived from the prior. Geostatistical estimator. In geostatistical models, sampled data is interpreted as a result of a random process. The fact that these models incorporate uncertainty in their conceptualization doesn't mean that the phenomenon, the forest, the aquifer, the mineral deposit, has resulted from a random process, but solely allows to build a methodological basis for the spatial inference of quantities in unobserved locations and to the quantification of the uncertainty associated with the estimator. A stochastic process is simply, in the context of this model, a way to approach the set of data collected from the samples. The first step in geostatistical modulation is the creation of a random process that best describes the set of experimental observed data. A value spatially located at is interpreted as a realization of the random variable. In the space, where the set of samples is dispersed, exists realizations of the random variables, correlated between themselves. The set of random variables constitutes a random function of which only one realization is known, the set of experimental data. With only one realization of each random variable, it's theoretically impossible to determine any statistical parameter of the individual variables or the function. The proposed solution in the geostatistical formalism consists in assuming various degrees of stationarity in the random function, in order to make possible the inference of some statistic values. For instance, if a work group of scientists assumes appropriate, based on the homogeneity of samples in area where the variable is distributed, the hypothesis that the first moment is stationary, then, they are implying that the mean can be estimated by the arithmetic mean of sampled values. Judging a hypothesis like this as appropriate is the same as considering that sample values are sufficiently homogeneous to validate that representativity. The hypothesis of stationarity related to the second moment is defined in the following way: the correlation between two random variables solely depends on the spatial distance that separates them and is independent of its location. Where this hypothesis allows to infer those two measures, the variogram and the covariogram, based on the samples. Where linear estimation, spatial inference, or estimation, of a quantity, at an unobserved location, is calculated from a linear combination of the observed values and weights. The weights are intended to summarize two extremely important procedures in a spatial inference process: reflect the structural proximity of samples to the estimation location. At the same time, they should have a desegregation effect, in order to avoid bias caused by eventual sample clusters. When calculating the weights, there are two objectives in the geostatistical formalism: unbiased and minimal variance of estimation. If the cloud of real values is plotted against the estimated values, the criterion for global unbiased, intrinsic stationarity or wide-sense stationarity of the field, implies that the mean of the estimations must be equal to mean of the real values. The second criterion says that the mean of the squared deviations must be minimal, which means that when the cloud of estimated values versus the cloud real values is more disperse, the estimator is more imprecise. Methods: depending on the stochastic properties of the random field and the various degrees of stationarity assumed, different methods for calculating the weights can be deducted, that is, different types of Kriging apply. Classical methods are: ordinary Kriging assumes stationarity of the first moment of all random variables, where is unknown. Simple Kriging assumes a known stationary mean, where is known. Universal Kriging assumes a general polynomial trend model, such as linear trend model. IRFK Kriging assumes to be an unknown polynomial in. Indicator Kriging uses indicator functions instead of the process itself, in order to estimate transition probabilities. Multiple indicator Kriging is a version of indicator Kriging working with a family of indicators. However, MIK has fallen out of favor as an interpolation technique in recent years. This is due to some inherent difficulties related to operation and model validation. Conditional simulation is fast becoming the accepted replacement technique in this case. Disjunctive Kriging is a nonlinear generalization of Kriging. Log-normal Kriging interpolates positive data by means of logarithms. Ordinary Kriging, the unknown value is interpreted as a random variable located in, as well as the values of neighbor samples. The estimator is also interpreted as a random variable located in, a result of the linear combination of variables. In order to deduce the Kriging system for the assumptions of the model, the following error committed while estimating in is declared. The two quality criteria referred previously can now be expressed in terms of the mean and variance of the new random variable, unbiased. Since the random function is stationary, the following constraint is observed. In order to ensure that the model is unbiased, the sum of weights needs to be 1. Minimal variance, minimize, two estimators can have, but the dispersion around their mean determines the difference between the quality of estimators. See covariance matrix for a detailed explanation. Where the literals stand for. Once defined the covariance model or variogram, or, valid in all field of analysis of, then we can write an expression for the estimation variance of any estimator and function of the covariance between the samples and the covariances between the samples and the point to estimate. Some conclusions can be asserted from this expression. The variance of estimation is not quantifiable to any linear estimator, once the stationarity of the mean and of the spatial covariances, or variograms, are assumed. Grows with the covariance between samples, that is to the same distance to the estimating point. If the samples are proximal to each other, then the clustering effect, or informational redundancy, is bigger, so the estimation is worst. This conclusion is valid to any value of the weights. A preferential grouping of samples is always worst, which means that for the same number of samples the estimation variance grows with the relative weight of the sample clusters. Grows when the covariance between the samples and the point to estimate decreases. This means that, when the samples are farther away from, the worse the estimation. Grows with the a priori variance of the variable. When the variable is less disperse, the variance is lower in any point of the area. Does not depend on the values of the samples. This means that the same spatial configuration always reproduces the same estimation variance in any part of the area. This way, the variance does not measure the uncertainty of estimation produced by the local variable. Kriging system. Solving this optimization problem results in the Kriging system. The additional parameter is a Lagrange multiplier used in the minimization of the Kriging error to honor the unbiasedness condition. Simple Kriging. Simple Kriging is mathematically the simplest, but the least general. It assumes the expectation of the random field to be known, and relies on a covariance function. However, in most applications neither the expectation nor the covariance are known beforehand. The practical assumptions for the application of simple Kriging are, wide-sense stationarity of the field. The expectation is zero everywhere. Known covariance function, Kriging system. The Kriging weights of simple Kriging have no unbiasedness condition and are given by the simple Kriging equation system. This is analogous to a linear regression of on the other. Estimation, the interpolation by simple Kriging is given by. The Kriging error is given by. Which leads to the generalized least squares version of the Gauss-Markov theorem. Properties, Krige 1993, Chiles and Delfiner 1999, Wackenagel 1995, the Kriging estimation is unbiased, the Kriging estimation honors the actually observed value, the Kriging estimation is the best linear unbiased estimator of if the assumptions hold. However, as with any method, if the assumptions do not hold, Kriging might be bad. There might be better nonlinear and or biased methods. No properties are guaranteed, when the wrong variogram is used. However, typically still a good interpolation is achieved. Best is not necessarily good, for example in case of no spatial dependence the Kriging interpolation is only as good as the arithmetic mean. Kriging provides as a measure of precision. However, this measure relies on the correctness of the variogram. Applications. Although Kriging was developed originally for applications in geostatistics, it is a general method of statistical interpolation that can be applied within any discipline to sample data from random fields that satisfy the appropriate mathematical assumptions. To date, Kriging has been used in a variety of disciplines, including the following: environmental science, hydrogeology, mining, natural resources, remote sensing, real estate appraisal, integrated circuit analysis and optimization, design and analysis of computer experiments. Another very important and rapidly growing field of application, in engineering, is the interpolation of data coming out as response variables of deterministic computer simulations, for example finite element method simulations. In this case, Kriging is used as a metamodeling tool, that is a black box model built over a design set of computer experiments. In many practical engineering problems, such as the design of a metal forming process, a single FEM simulation might be several hours or even a few days long. It is therefore more efficient to design and run a limited number of computer simulations, and then use a Kriging interpolator to rapidly predict the response in any other design point. Kriging is therefore used very often as a so-called surrogate model, implemented inside optimization routines. Resources, books, Abramowitz, M., and Stegun, I., Handbook of Mathematical Functions, Dover Publications, New York. Danie G, S., Carlin, B.P. and Gelfand, A.E. Hierarchical Modeling and Analysis for Spatial Data. Chapman and Hall CRC Press, Taylor and Francis Group. Chiles, J.P. and P. Delfiner Geostatistics, Modeling Spatial Uncertainty. Wiley Series in Probability and Statistics. Krige, N. Statistics for Spatial Data, Wiley, New York, David, M. Handbook of Applied Advanced Geostatistical or Reserve Estimation, Elsevier Scientific Publishing, Deutsch, CV, and Journal, AG, GSLIB, Geostatistical Software Library and User's Guide, Oxford University Press, New York, 338 pp. Guvarts, P. Geostatistics for Natural Resources Evaluation, Oxford University Press, New York. ISBN 0-511,538-4, Isaacs, E.H., and Srivastava, R.M., An Introduction to Applied Geostatistics, Oxford University Press, New York, 561 pp. Journal, A.G. and C.J. Huybrechts Mining Geostatistics, Academic Press London, Journal, A.G., Fundamentals of Geostatistics and 5 Lessons, American Geophysical Union, Washington, D.C., Press, W.H. Tucholsky, S.A. Bettling, W.T. Flannery, B.P., Section 3.7.4. Interpolation by Kriging, Numerical Recipes, The Art of Scientific Computing, New York, Cambridge University Press, ISBN A978-0-521-88068-8A. Also, Section 15.9. Gaussian Process Regression. Source, A. Geostatistica para Asia NCIA Estar Terra e do Ambiente, IST Press, Lisbon, ISBN 972-8469-46-2, Stein, M.L., Statistical Interpolation of Spatial Data, Some Theory for Kriging, Springer, New York. Wackenagel, H. Multivariate Geostatistics, An Introduction with Applications, Springer Berlin, Software, R Packages, GSTAT, Spatial and Spatiotemporal Geostatistical Modeling, Prediction and Simulation, Random Fields, Simulation and Analysis of Random Fields, BACCO, Bayesian Analysis of Computer Code Software, TGP, Treat Gaussian Processes, DICE Design, DICE Eval, DICE Kriging, DICE Optim, Mutamodeling Packages of the DICE Consortium, MATLAB GNU Octave, MGSTAT, Geostatistics Toolbox for MATLAB. DACE, Design and Analysis of Computer Experiments. A MATLAB Kriging Toolbox. GPML, Gaussian Processes for Machine Learning. STK, Small Toolbox for Kriging for Design and Analysis of Computer Experiments. Scala Gauss, MATLAB Kriging Toolbox with a focus on large datasets, Scilab, DACE Scilab, Scilab port of the DACE Kriging MATLAB Toolbox, Krige, Kriging Toolbox for Scilab, KRISP, Kriging-based regression and optimization package for Scilab, Python, scikit-learn, machine learning in Python, see also, Bayes linear statistics, Gaussian process, multiple indicator Kriging, spatial dependence, variogram, multivariate interpolation, radial basis function, references, Gracewuchter. Spline models for observational data 59. Siam. PA 162. Williams, CKI prediction with Gaussian processes, from linear regression to linear prediction and beyond. Learning in graphical models PPA 599 Euro 621 doi, 10.1007 over 978-94-011-5014-923. ISBN A978-94-010-6104-9. Source 2006, pages 18, Matheron G. 1978, Heinvi Berakta and F. Caesar. Churelioglu, a Kriging-based approach for locating a sampling Satia Euro in the assessment of air quality, SERRA, 19, 301-305 doi, 10.1007 per second 00477-005-0234-8, Chiles, J.P. and P. Delphina Geostatistics, Modeling Spatial Uncertainty, Wiley Series in Probability and Statistics. Zimmerman, D.A. De Marzilli, G. Gotway, C.A. Marietta, M.G. Axness, C.L. Beheim, R.L. Braz, R.L. Carrera, J. Dagan, G. Davis, P.B. Gallegos, D.P. Galley, A. Gar-Cubed-Mes Hernandez, J. Grindrod, P. Gertjar, A.L. Katanidis, P.K. Lavenue, A.M. McLaughlin, D. Newman, S.P. Ramarao, B.S. Ravan, C. Rubin, Y.A. Comparison of 7 geostatistically based inverse approaches to estimate transmissivities for modeling advocative transport by groundwater flow. Water Resources Research 34, 1373. doi, 10.1029/98WR00003 Tonkin, M.J. Larson, S.P. Kriging water levels with a regional linear and point logarithmic drift. Groundwater 40, 185 euro 193 doi, 10.1111 per joule 1745-6584.2002 TBO2503X. PMIDA 11916123 Journal, A.G. and C.J. Hoebrechts Mining Geostatistics, Academic Press London, Richmond, A Financially Efficient or Selections Incorporating Grade Uncertainty. Mathematical Geology 35, 195 euro 215 doi, 10.1023 per hour, 1,023,239,606,028 Guvalets Geostatistics for Natural Resource Evaluation, OUP. ISBN 0-19-511538-4, Emery, X. Simple and Ordinary Multi-Gaussian Kriging for Estimating Recoverable Reserves. Mathematical Geology 37, 295 euro 319 doi, 10.1007 per second 11004-005-1560-6 Paprites, A. Stein, A Spatial Prediction by Linear Kriging. Spatial Statistics for Remote Sensing. Remote Sensing and Digital Image Processing 1. PA 83 doi, 10.1007/-306-47647-96. ISBN A0-7923-5978-X. Barris, J. An Expert System for Appraisal by the Method of Comparison. PhD Thesis, UPC, Barcelona, Barris, J. and Garcia Almiral, P. 2010, A Density Function of the Appraisal Value, UPC, Barcelona, Oganakauho Okobia, Saradio Monti, and Elias Cargiano's Geostatistical Inspired Fast Layout Optimization of a Nano-CMOS Thermal Sensor, IET Circuits, Devices and Systems, Volume 7, No. 5, September 2013, pages 253, 262. Sachs, J. and Welch, W. J. and Mitchell, T. J. and Wynne, H.P. Design and Analysis of Computer Experiments 4. Statistical Science PPA 409 euro 435 Strono, M.A. Technique for FEM Optimization under Reliability Constraint of Process Variables in Sheet Metal Forming. International Journal of Material Forming 1, 13 euro 20 doi, 10.1007 per second 12289-008-0001-8 Historical References, Agterberg, F.P., Geomathematics, Mathematical Background and Geoscience Applications, Elsevier Scientific Publishing Company, Amsterdam, 1974, Krige, N.A.C., The Origins of Kriging, Mathematical Geology, v. 22, pages 239 euro 252, 1990, Krige, D. G., A Statistical Approach to Some Mine Valuations and Allied Problems at the Witwatersrand, Master's Thesis of the University of Witwatersrand, 1951 Link, R.F. and Koch, G.S., Experimental Designs and Trend Surface Analysis, Geostatistics, A Colloquium, Plenum Press, New York, 1970, Matheron, G., Principles of Geostatistics, Economic Geology, 58, pages 1246 euro 1266, 1963, Matheron, G., The Intrinsic Random Functions, and Their Applications, ADV. APPL. Prob. 5, pages 439 a Euro 468, 1973, Merriam, D.F., editor, Geostatistics, A Colloquium, Plenum Press, New York, 1970.